You know, have you ever sat under one of those huge ceiling fans, maybe at a restaurant or in a big open space, and you get that little nagging thought, like, is that thing really secure up there? Well, you're not the only one. And today we're going to pull back the curtain on the amazing and pretty intense science that makes sure you can just sit back and relax. So, our story kicks off at the British school in Jakarta. They had a really simple goal. They wanted to put up some new, powerful industrial fans in their outdoor eating areas, to keep the students cool. Great idea, makes total sense. But that brings up a huge engineering question, right? You can't just drill a few holes in the ceiling and hope for the best. We're talking about adding a pretty heavy, moving weight to a building that wasn't designed with it in mind from day one. So, how can you be absolutely 100% sure it's safe?
Well, the answer, as it turns out, is with a ton of science. And hey, just to put your mind at ease right away, the final conclusion from the super detailed engineering report was a big, clear, yes, it is perfectly safe. Okay, so now let's dive in and see exactly how they figured that out.
The whole thing starts not with computers or fancy software, but with some real hands-on detective work. And that brings us to our first section, checking the building's bones. So before a single calculation was even made, engineers had to get out there, on site, and really understand the actual condition of the building as it stood. They needed to know what the true strength of the concrete was and what exactly was going on inside it. To do this, they used three main methods. First, something called an ultrasonic pulse velocity test. That's to check the quality of the concrete. Second, a cover meter test, to basically map out the steel reinforcing bars, the rebar, hiding inside. And finally, some very careful chipping to physically see and measure that rebar. Now, those first two methods fall under this fascinating category called non-destructive testing, or NDT. It's just a brilliant way to check a structure's health without actually hurting it. The best way to think of it? It's like giving the building a medical ultrasound. Okay, so with all that crucial real-world data in hand, the team was ready for the next big phase. Let's move on to Section 2, building a digital twin. The process got started with the building's original blueprints, the architectural DNA for the two buildings where the fans were going to go. Then they took these plans and they mixed them with all that data they just collected on site. The actual concrete strength, the precise locations of the rebar, all of this info got plugged into this really sophisticated software called ETABS, which is basically designed to simulate how buildings act under stress. And this let them create a super accurate 3D model, a true digital twin of the real building. And here's where it gets really, really cool. Once you have a perfect digital copy of a building, you can do things to it that you could never do in real life. Which brings us to Section 3, the virtual stress test. So this is the object at the heart of our story, the Air Pro 400. It's a big, commercial-grade fan, almost 4 meters in diameter. It's a serious piece of equipment. Now, according to the manufacturer's own specs, the total weight of one fan assembly is 55 kilograms. That's about 121 pounds. I mean, that's a decent amount of weight to just hang from a ceiling. And this is so important, the engineers didn't test the structure for just 55 kilograms. No way. In their virtual model, they cranked it up and applied a load of 220 kilograms for each fan. That's almost 500 pounds. And this is just a perfect example of a core principle of engineering. The official report states it right there. The fan manufacturer requires a safety factor of 4. So the test load is 4 times the actual weight. This is to account for any dynamic forces, vibration, and just to create a massive, massive margin of safety. So the digital twin is ready. The huge virtual load is hanging from the ceiling. Did the building pass the test? Let's find out in Section 4, passing the safety test. All right, so the first thing engineers check for is something called deflection. And to put it simply, that's just how much a beam bends or sags when you hang weight from it. And there are very strict rules about how much bending is safe. And the results were, they were remarkable. According to the building codes, the absolute maximum bend allowed for this beam was 15.6 millimeters. So when the engineers applied that full 220 kilogram test load in the model, the actual bend was just 2.6 millimeters. I mean, it barely even moved. A total overwhelming pass. Next up, they checked the columns that are holding those beams up. And for this, they use a measure called the PMM ratio. Now, it's a bit complex, but the easiest way to think of it is as an overall safety score.
It combines all the different forces on a column, pushing, pulling, bending, and the rule is simple. That score has to stay below 1.0.
And, you guessed it, the buildings passed with flying colors. The analysis showed that every single column they looked at had a PMM ratio way, way below that 1.0 safety limit. It just confirmed they had more than enough strength to handle the new load. So after all the detective work on site, the digital modeling, and those intense virtual stress tests, we finally arrive at the verdict. Which brings us to our last section, engineering for peace of mind. The final report was totally conclusive. It said, very clearly, that the buildings were more than strong enough and no changes were needed. The big takeaway? The school got the green light. The fan installation could go ahead safely. And that's really the big picture here. This whole careful process, this is the hidden engineering that's all around us, keeping us safe in the buildings we live, work, and learn in every single day. It's the reason we can look up at a giant ceiling fan and just not have to worry about it. And it kind of leaves you with a final thought, right? The next time you're out and about, just take a look around you. A balcony, a huge light fixture, a scoreboard at a stadium. What other things that seem so simple are actually held in place by this same invisible level of really complex and fascinating science?